Here we have first question. Complete table 1.1 by stating whether each of the quantities is a vector or a scalar. Right. So here we have the quantities, and in this box we'll list if they are vectors or scalars. So first, let's see acceleration. Well, we know that acceleration is defined as the time rate of change of velocity, right? And we know velocity is a vector quantity, which means acceleration should also be a vector quantity. The acceleration is in the direction of the change in velocity. So acceleration is a vector. Next, we have electrical resistance. Resistance is just a number that tells you how strong are we restricting the flow of electrons or charges in a wire, for example, right? And it does not really have to do with any direction. The direction does not change the physics behind it, and therefore it is a scalar quantity. And finally, we have momentum, and momentum is defined as the product of mass times velocity. Now, mass is just a constant, velocity is a vector, and so momentum is in the direction of the velocity of the object. So this means that momentum is also a vector quantity. All right, next we have part B to the question that says that state the conditions for an object to be in an equilibrium. Now there are two types of equilibriums, right? So the first one equilibrium is a translational equilibrium, where if I have an object like this and I apply a force in this direction, and there is an equal but opposite force in the other direction, right? So the direction is shown by these arrows. In this case, and if there are no other forces acting on this, then it is said to be in a translational equilibrium. It's not moving translationally, right? And if I have something where I can perform rotations, so if I take a rod and pivot it at the center, for example, and now there are some forces acting on it, something like this, so what will happen is that this will tend to rotate in this direction, and if the turning effect is balanced, then it is said to be in a rotational equilibrium as well. And for an object to be in an equilibrium, as in a complete equilibrium, it has to be in both of these equilibriums together, right? So the conditions for an object to be in an equilibrium are basically two, one coming from the translational equilibrium and the other one coming from the rotational equilibrium. And so the translational equilibrium should satisfy this thing, that the resultant sum of the forces, all of the forces that are acting on the system, are zero, right? Which you can write it in words as resultant force is acting on a body vanishes, right? Or is zero. So that is translational equilibrium. Now, the next one is the rotational equilibrium, and for a rotational equilibrium to be maintained, the sum of all the clockwise moments should be balanced by the sum of all anti-clockwise moments. Now, moments is just a physical way of quantifying the turning effect that was happening in this figure too, right? So here you can see this is the clockwise moment, right? And this is the anti-clockwise moment. So the sum of all the clockwise moments are equal to sum of all the anti-clockwise moments, which you can also write down mathematically as sum of, if I represent moments like this, so anti-clockwise is equal to sum of clockwise moments. All right. So next part, we have a floating cylinder, and it's attached by a wire to the seabed as shown in this figure. So we can see that this is the floating cylinder. It's attached by a wire, and the distance that it's dipped in this seabed is 0.190 meters. This is the surface of the water. That's the seabed. The density of water is also specified, and the weight of the cylinder is given as 28 newtons, which means that there will be a constant force acting downwards of 28 newtons. Now the density of water is this: the base of the cylinder is at the depth of 0.190 meters below the surface of the water. The cylinder has a weight of 28 newtons and a cross-sectional area of 0.0230 meters squared. So the cross-sectional area is also provided for the cylinder. The wire and the central axis of the cylinder are both vertical. The cylinder is in equilibrium. So that's the problem statement, and we are required to calculate the three significant figures: the upthrust acting on the cylinder due to water, right? So if you come back to the figure, you see that if the cylinder is dipped in this water, then there is an opposite force acting on this cylinder as well from the water, and that force is basically what they're calling the upthrust from the water, right? Now, why is this upthrust caused? Because in water, when I add the cylinder, I'm basically changing the pressure of the water. I'm inserting more pressure on the water by putting the cylinder in, and that difference or that change in pressure is the reason for this upthrust force to be present over here, right? So if you go back here, that means that the upthrust is equal to change in pressure, or you can say it is caused by change in pressure. So then it's pretty straightforward to compute this result as writing down the equation for the force of for an object that is submerged in the water as change in height times the density of the water times the acceleration due to gravity. It's on Earth's surface, so the acceleration due to gravity would be 9.81, and this is basically the pressure, and you will multiply this with area to get force, because if you remember, pressure is force exerted per unit area, right? So this upthrust is the force, and now you just put in the values. Remember, the change in height is this height, that is, it is dipped in the water, and that's 0.190 meters. So 0.190 meters times the density of the water, which was 1.0 into 10 raised to power 3, and we'll multiply that with the acceleration due to gravity, which is 9.81. And the cross-sectional area, which is also provided in the problem statement, is 0.0230. Now, it's just a matter of doing the math, and once you do that, you get 42.9 newtons. And I rounded this off to three significant figures as it was stated in the problem. So this is the first significant figure, this is the second, and this is the third significant figure, right? So the answer to this problem is 42.9 newtons of upthrust, which is acting on the cylinder due to the water, right? Which is again due to the pressure difference caused by the cylinder. Right. Next is that show that the tension T in the wire is 15 newtons, right? So if I go back to this diagram, I have computed this upthrust, right? And now I'll write its value, which is 42.9 newtons. Now there is weight of the cylinder acting downwards, and there is upthrust which is acting upwards. Now if this cylinder is attached with this rope, then there will be a tension built into this rope which will be acting in this direction, right? Now this is the tension that we want to figure out. So you can see that if I remember that this is in an equilibrium, then I can immediately use this relation that sum of all the forces in one direction should be equal to sum of all the forces in the other direction, right? So let me write it down. Basically what I mean is opposite direction, right? Which means that I can rewrite this an equation for this thing as that the two forces that are acting in the same direction are tension and the upthrust. So this gives me tension plus upthrust, which should be equal to the opposite direction force, which is the weight, right? So W. So this is the equation that I just made. And now we'll use this equation to figure out the tension in the string on the next page. So the equation that we have is U plus T is equal to W. U is the upthrust, which is 42.9 newtons, plus the tension that we want to figure out, and the weight of this thing is 28 newtons again. So the tension, rearranging this, would be 14.9 newtons, right? And you can round this off to 15 newtons, right? And you have shown this thing. All right. So the next part says that the wire has a cross-sectional area of this. Calculate the stress in the wire, right? So that's also pretty straightforward. Now, this is the cross-sectional area of this wire, right? So it is this area that the wire is having, and we know the tension in the wire, right? And we are required to figure out the stress. Now, tension is a type of force, right? So if it's a type of force, we remember that the stress is defined as force applied per unit area, right? Now, this should be equal to the force, which is the tension in the string, divided by the area of the wire, which is, as we figured out, the tension is 15 newtons, and the area is 3.2 millimeters squared, right? So we have to get rid of this milli. We know that a milli, this is basically, this M is for milli, so I'll write it like this. This milli just means it's a prefix of 10 raised to power minus 3. And so milli squared should be then 10 raised to power minus 6, right? And so I'll just replace this milli with 10 raised to power minus 3 squared, this milli squared, because this millimeter, the square is acting on entire unit, millimeters. So 3.2 into 10 raised to power minus 3, and then square this, which would be 10 raised to power minus 6, and then do the math. This is meters, so this would give you 4.69 into 10 raised to power 6 pascals, right? So because the units Newton per meter, these units are defined as a single unit, which is pascal. So the stress in this wire is 4.69 into 10 raised to power 6 pascals. Now, the part 4 of the problem states that the surface of the water gradually rises until it's level with the top surface of the cylinder. State and explain qualitatively the variation of strain energy stored in the wire as the water surface rises, right? So basically, we know that in an equilibrium state, we saw that the equation that we had was upthrust. The sum of upthrust and tension was balancing the weight of the cylinder. So since the weight is constant, the upthrust is going to increase, right? And why is it going to increase? Because of the depth of the liquid, right? So if you go deeper and deeper, the upthrust is going to increase and increase and increase. And if that increases, the upthrust is increasing, that means that the tension should also be increasing. And if the tension increases, then clearly the strain energy that is stored is going to increase. So we can say something like that weight is constant. So if the upthrust increases due to increase in pressure, increase in the depth, right? That means that the tension in the string will increase, right? And if that increases, that just implies that the strain energy increases, right? Because the strain energy depends upon the stress, and if the tension increases, then the stress is going to increase, and if that happens, then the strain energy stored will be increased.